March 1941. Mare Island Naval Shipyard, Vallejo, California. Ted Nelson, employee number 3872, watched 12 men disappear beneath a submarine hull, crawling into scaffolding that would consume the next 5 to 7 days of their lives. The mathematics were simple and infuriating. 12 skilled workers. 140 hours of combined labor. A single wooden deck that could have been installed in a fraction of the time, if anyone cared to question how things had always been done. What Nelson understood that morning, standing in Building 46, earning his $11 per day, would eventually save the United States Navy 50 million man-hours during World War II. But first, the Navy would have to fire him. The traditional deck installation method represented everything wrong with industrial processes that survived through institutional inertia rather than logical efficiency. Workers constructed elaborate scaffolding systems beneath submarine hulls, creating cramped, dangerous workspaces filled with metal dust and inadequate ventilation. From these confined positions, they drilled holes upward through steel plating, threaded bolts through the openings, then climbed topside to secure wooden planking. The process required precise coordination between teams working above and below the hull. Any misalignment meant starting over. Every submarine waited its turn for this bottleneck operation, while other construction phases sat idle. Mare Island in early 1941 operated at the threshold of crisis without yet recognizing it. Founded in 1854 by Commander David Glasgow Farragut as America's first Pacific naval facility, the shipyard had evolved into a critical component of national defense infrastructure. 12,000 workers maintained 3-shift operations 7 days per week, responding to escalating tensions with Japan that made every vessel urgently necessary. Production schedules were aggressive, but achievable under normal circumstances. The deck installation bottleneck, however, represented anything but normal circumstances. It was systematic waste, encoded into standard operating procedures, accepted because no one had successfully challenged it. Nelson brought 15 years of California machine shop experience to his position at Mare Island. His background had exposed him to stud welding technology, a process using intense electrical current to fuse metal studs directly to surfaces. The technology worked brilliantly on horizontal applications where gravity cooperated, allowing ceramic flux powder to settle properly and protect the molten weld. Attempt the same process on vertical or overhead surfaces, and the flux powder simply fell away before the weld completed, leaving weak, contaminated connections. The limitation appeared absolute. Stud welding required gravity's cooperation. Every welding engineer accepted this fundamental constraint. Nelson saw something different. The flux powder did not need to fall. A ceramic cap could contain it during the welding process, regardless of surface orientation. The stud would weld directly through the ceramic barrier, which would then break away cleanly. No scaffolding beneath the hull, no drilling from below, no threading bolts through steel. Position the stud. Activate the welder. Move forward. What consumed 12 men for a week might require 4 workers for a single day. He sketched the design that evening. The next morning, he presented his solution to Navy supervisors. Their response would transform his life in ways he could not have anticipated. The Navy supervisors examined Nelson's sketches with the practiced courtesy of men accustomed to evaluating worker suggestions. They studied his calculations, demonstrating time savings. They reviewed his technical drawings showing the ceramic cap design. Then they delivered their verdict with the casual finality that only established institutional authority can produce. The proposal was impractical for submarine construction. The technology remained unproven in critical naval applications. The traditional bolt-through method had functioned reliably for decades, and Mare Island operated under strict Bureau of Ships specifications that could not be modified by local supervisors regardless of potential efficiency gains. Even if Nelson's invention performed exactly as promised, implementing it would require documentation, testing protocols, and approval processes that could consume months or years. The Navy procurement system existed for valid reasons. Individual workers proposing revolutionary changes to established construction methods, however well-intentioned, did not override institutional procedures designed to ensure quality and reliability. Nelson pressed his case with increasing urgency. He explained that the ceramic cap would contain flux powder during overhead welding operations, solving the fundamental limitation that had always prevented stud welding on vertical surfaces. He demonstrated through calculations that deck installation time could decrease from 5 days to potentially 8 hours. He emphasized that the technology could accelerate submarine delivery schedules precisely when escalating Pacific tensions made every vessel critically important. The supervisors remained unmoved. Beyond the procedural obstacles, there existed an unspoken but powerful assumption about where technical innovation originated. Nelson was a machinist earning $11 per day, not a degreed engineer from a prestigious university. The Navy's technical decisions came from Annapolis graduates and credentialed civilian engineers whose expertise was validated by formal training and professional standing. A shop floor worker proposing fundamental changes to naval construction methods violated hierarchical expectations about the proper channels for technical advancement. The meeting concluded with polite acknowledgement that Nelson's enthusiasm was noted, but Mare Island would continue following established procedures. The supervisors returned to managing the 12,000 workers under their authority. Nelson returned to his workstation, understanding that he faced an immovable institutional barrier. He was 36 years old with 15 years of machinist experience, a few $100s in savings, and an invention that could save millions of man-hours in wartime production. He possessed no formal engineering credentials, no connections to Navy procurement officials, and no authority to implement changes to standard operating procedures. The logical response would have been acceptance. A reasonable man would have collected his daily wage and abandoned aspirations of revolutionizing shipyard operations. Nelson submitted his resignation later that week. Mare Island personnel records noted the departure of employee number 3,872 without ceremony. The Navy had no way of knowing they had just rejected the man who would eventually save them 50 million man-hours, receive the Army-Navy Excellence Award, and fundamentally transform industrial welding practices for the remainder of the 20th century. What the supervisors dismissed as an impractical garage invention would return to Mare Island within months, but under circumstances that would make rejection impossible. Nelson's garage in Vallejo transformed into an improvised manufacturing laboratory during the spring of 1941. The space that had previously housed an automobile now contained a workbench assembled from scrap lumber, welding equipment purchased with rapidly diminishing savings, and boxes of ceramic materials acquired from suppliers who questioned why a lone machinist needed industrial quantities of specialized flux compounds. The technical challenge proved more complex than his initial sketches had suggested. The ceramic cap required precise material properties that existed within narrow parameters. The ceramic needed sufficient structural integrity to withstand intense electrical current without shattering prematurely, yet enough controlled brittleness to fracture cleanly after the weld completed. The flux powder composition demanded exact calibration. Excessive flux contaminated the weld with impurities that weakened the metal bond. Insufficient flux exposed molten metal to atmospheric oxygen and nitrogen, creating porosity and reducing connection strength. The electrical timing parameters required experimentation, to determine optimal current duration and amperage levels for different stud sizes and base metal thicknesses. Nelson conducted systematic testing throughout April and May, documenting each failure and adjustment. Neighbors grew accustomed to seeing light emanating from his garage past midnight, hearing the sharp crack of welding equipment, observing him emerge covered in ceramic dust and metal residue. The financial pressure intensified with each material purchase and each day without income. He had walked away from $11 in daily wages and steady employment in an expanding wartime economy to pursue an idea that Navy supervisors had dismissed as impractical. Friends from Mare Island visited occasionally, their concern evident beneath casual conversation. When would he acknowledge defeat and return to shipyard work? How long could he sustain expensive experimentation without revenue? Nelson's response remained consistent. The technology would function as designed. The underlying physics were sound. The challenge was not whether ceramic caps could contain flux powder during overhead welding, but rather discovering the precise combination of materials and electrical parameters that would make the process reliable under production conditions. By late May, he had achieved consistent results on test pieces. The ceramic caps held flux powder in position regardless of welding angle. The electrical current fused studs to base metal with strength exceeding traditional bolt-through connections. The ceramic fractured cleanly, leaving welds that required no finishing work. The entire process consumed seconds rather than hours. Nelson began manufacturing ceramic caps in larger quantities, refining his production methods to achieve consistency. He purchased a used truck and started visiting industrial facilities around the San Francisco Bay Area, demonstrating his stud welding system to plant managers and production supervisors. The responses provided validation. Several companies placed small orders for specialized welding applications. Nelson had not yet achieved profitability, but he was generating revenue, proving that his technology possessed commercial value beyond his original submarine decking application. Then, December 7th, 1941 arrived. Japanese aircraft attacked Pearl Harbor. America entered World War II, and the entire nation mobilized for industrial warfare on a scale that would dwarf all previous conflicts. Suddenly, every shipyard, every factory, every production facility faced desperate pressure to increase output. Speed became the paramount consideration. Efficiency became survival. Nelson recognized his moment had arrived. The attack on Pearl Harbor transformed American industrial priorities with immediate and total effect. Mare Island Naval Shipyard, which had employed 12,000 workers in March when Nelson departed, was expanding toward a workforce that would eventually reach 50,000 by 1944. The submarine construction bay, where Nelson had once worked as employee number 3,872, now operated at maximum capacity, with vessels moving through production stages as rapidly as workers could complete them. The deck installation bottleneck that he had identified 9 months earlier had evolved from inefficiency into crisis. Every hour consumed on traditional scaffolding and bolt-through methods was an hour that delayed a submarine from reaching the Pacific theater where American forces desperately needed naval reinforcements. Nelson returned to Mare Island in January 1942, but his status had fundamentally changed. He arrived not as a worker seeking re-employment, but as the proprietor of a welding technology company, carrying demonstration equipment, documented test results, and confidence born from months of successful experimentation. The supervisors who had dismissed his proposal in March now confronted a radically different strategic environment. The Navy no longer evaluated proposals with peacetime deliberation. Production acceleration had become a matter of national survival, and institutional procedures that might have delayed adoption for months were compressed into days by wartime urgency. The demonstration took place in Building 46, the same facility where Nelson had originally conceived his design. He positioned his equipment on a section of vertical steel plate, loaded a ceramic-capped stud into the welding gun, and triggered the electrical current. The process consumed approximately 3 seconds. The ceramic cap shattered cleanly away, revealing a weld that subsequent inspection confirmed met or exceeded the strength specifications of traditional bolt-through connections. He repeated the demonstration on overhead surfaces, on angled plates, on positions where conventional stud welding had always failed due to flux powder displacement caused by gravity. The Navy engineers observing the demonstration understood immediately what they were witnessing. This represented not merely incremental improvement to existing technology, but rather the elimination of an entire construction phase that consumed days of skilled labor. A submarine deck that required 12 men working 5 to 7 days could potentially be completed by 4 workers in a single shift. The time savings compounded across every vessel under construction simultaneously at Mare Island and other Pacific shipyards. Applied to the production schedules already straining under wartime demand, the technology could accelerate submarine delivery by weeks per vessel. Nelson received his first Navy contract within days. The terms were modest compared to what would follow, but the validation was absolute. The institution that had rejected his proposal now urgently wanted to implement it across their Pacific shipbuilding facilities. Mare Island would serve as the initial testing ground, with rapid expansion to other facilities contingent on production results matching demonstration promises. Nelson moved immediately to scale his operation. His garage workshop was already inadequate for the manufacturing demands that a Navy contract would generate. He incorporated his business formally in March 1942, establishing production facilities capable of manufacturing both the consumable ceramic caps and the specialized welding equipment required for implementation. The success at Mare Island attracted immediate attention from Navy procurement officers monitoring production bottlenecks across the Pacific shipbuilding complex. By summer 1942, Nelson's stud welding system was being evaluated at naval facilities from Puget Sound to San Diego. The technology that had solved the submarine decking problem revealed applications extending far beyond its original purpose, demonstrating a versatility that neither Nelson nor the Navy had initially anticipated. Destroyers required thousands of welded connections for equipment mounting, pipe brackets, and structural reinforcements throughout their construction. Traditional methods demanded drilling through steel plate, tapping threads into the holes, and installing bolts with precise torque specifications for each individual connection point. Nelson's system eliminated multiple procedural steps, reducing installation time by factors of 10 or more for many applications. The process produced stronger connections that better distributed mechanical stress, created no structural weakening from drilled holes, and required fewer skilled workers to accomplish equivalent tasks. Aircraft carriers presented even more dramatic opportunities for implementation. These massive vessels contained countless systems requiring secure mounting points for electrical conduits, ventilation ducts, damage control equipment, and communication systems distributed throughout the ship. Each mounting point had traditionally meant drilling through steel plate, a process that compromised structural integrity while consuming hours of labor. Stud welding preserved the plate's original strength characteristics while accelerating installation schedules that had previously consumed weeks of fitting-out work. The technology spread beyond naval construction into merchant shipbuilding, where Liberty ships were being produced at unprecedented rates to replace vessels lost to German submarine attacks. These cargo vessels, designed specifically for rapid mass production using simplified construction methods, benefited enormously from any process that reduced construction time without compromising structural integrity. Henry Kaiser's shipyards on the West Coast, already famous for revolutionary prefabrication techniques, incorporated Nelson's stud welding into their production lines. The combination of modular construction and rapid welding technology drove Liberty ship construction times to levels that seemed impossible by traditional shipbuilding standards. By late 1942, Nelson's company was manufacturing thousands of ceramic caps monthly and producing welding equipment as rapidly as factory capacity allowed. The original garage operation had evolved into a legitimate industrial manufacturer, employing dozens of workers across multiple production shifts. The company's growth trajectory was constrained primarily by the availability of skilled labor and raw materials in a wartime economy, where every resource faced competing demands from various defense production sectors. The Bureau of Ships began documenting the productivity improvements with systematic rigor. Internal reports calculated that Nelson's technology saved approximately 8 man-hours per stud installation compared to traditional bolt-through methods. Across the thousands of installations required for a single major warship, the savings accumulated to hundreds or thousands of man-hours per vessel. Multiplied across the scores of ships under simultaneous construction at American shipyards, the aggregate impact reached into millions of man-hours by the end of 1942, with projections suggesting the savings would continue accelerating as more facilities adopted the technology and expanded its applications. The Army-Navy Excellence Award represented the highest recognition the United States government could bestow on civilian production facilities during World War II. The award signified exceptional performance in production quality, quantity, and innovation that materially contributed to the war effort. Companies receiving this distinction displayed the award flag prominently as tangible evidence that their contribution had achieved standards exceeding normal expectations. In May 1944, Nelson's company received this honor at ceremonies held at their San Leandro, California manufacturing plant, validating the transformation from garage workshop to essential defense contractor. The citation accompanying the award detailed specific contributions that had earned the recognition. The stud welding technology had by this point saved an estimated 50 million man-hours across American war production. This figure was not promotional exaggeration or optimistic projection, but rather the result of systematic analysis conducted by War Production Board statisticians who had tracked productivity improvements at facilities implementing the technology since early 1942. 50 million man-hours represented the equivalent of 25,000 workers laboring full-time for an entire year. In a wartime economy, where skilled labor constituted the scarcest and most valuable resource, this contribution possessed significance comparable to constructing entirely new production facilities. The calculation methodology employed straightforward mathematical principles. Each stud installation using Nelson's ceramic cap system saved approximately 8 man-hours compared to traditional drilling and bolt-through methods that required scaffolding construction, precise positioning from multiple angles, and coordination between workers operating above and below the connection point. War Production Board records documented that by May 1944, Nelson's technology had been implemented for approximately 6 million stud installations across naval shipyards, merchant ship construction facilities, tank manufacturing plants, and aircraft assembly operations. The multiplication yielded approximately 48 million man-hours saved, a figure that would continue growing as the technology spread to additional applications and production facilities throughout the remainder of the war. The ceremony at San Leandro drew representatives from the Navy Bureau of Ships, the War Production Board, and congressional delegations from California, who recognized the political value of celebrating wartime industrial achievement. Captain James Richardson, representing the Bureau of Ships, delivered remarks emphasizing that technological innovation constituted as critical a contribution to victory as battlefield courage. He noted specifically that Nelson's invention had accelerated ship delivery schedules by weeks per vessel, multiplying American naval capacity at the precise historical moment when Pacific operations demanded maximum fleet strength to sustain offensive operations across vast oceanic distances. The award citation also acknowledged secondary innovations that Nelson had developed after his initial ceramic cap design. He had refined the electrical timing mechanisms in his welding equipment, creating what became known as the drawn arc stud welding process. This advancement improved weld quality consistency and extended the range of materials that could be joined successfully using the technology. The combination of the ceramic cap innovation and the drawn arc process created a welding system that was simultaneously more versatile and more reliable than any previously available alternative technology. The impact of Nelson's stud welding technology extended far beyond the naval shipyards, where it had first proven its value. By mid-1944, the innovation had permeated American war production across multiple industries, fundamentally altering manufacturing processes that had remained unchanged for generations. The technology represented not merely incremental improvement, but rather a paradigm shift in how metal fabrication could be accomplished under the intense pressures of wartime production schedules. The Pacific Paratrooper program, which required rapid production of specialized aircraft for airborne operations, adopted Nelson's system for securing equipment mounts and structural reinforcements throughout the airframe. Aircraft manufacturing had traditionally been one of the most labor-intensive sectors of war production, with each plane requiring thousands of individual fastening operations performed by skilled workers. The ability to weld studs directly through fuselage skin without drilling or threading holes reduced assembly time while simultaneously improving structural integrity. Engineers discovered that stud-welded connections distributed stress more evenly than bolted joints, an unexpected benefit that enhanced aircraft durability under combat conditions where vibration, impact forces, and material fatigue posed constant threats to structural reliability. Tank manufacturing facilities faced similar challenges with traditional fastening methods that consumed excessive labor hours. The M4 Sherman tank alone required several thousand mounting points for interior equipment, armor attachments, and mechanical systems distributed throughout the vehicle. Each mounting point had historically demanded drilling through hardened steel, tapping threads with precision tools, and installing bolts with exact torque specifications to prevent loosening under combat vibration. Nelson's technology eliminated the drilling phase entirely and created connections that could withstand the extreme vibration and shock loads that armored vehicles experienced during combat operations across varied terrain. Production supervisors at tank plants reported that fitting-out time for interior equipment installation decreased by approximately 30% after implementing the stud welding system, allowing the same workforce to complete more vehicles within identical time periods. The technology found applications in industries that had no direct military connection, but were nonetheless critical to the war effort. Bridge construction for military transportation routes required thousands of connection points, where traditional drilling through structural steel consumed weeks of skilled labor. Power generation facilities for defense plants needed rapid installation of equipment mounts and cable supports. Petroleum refinery expansions required secure mounting systems for piping networks and processing equipment. The versatility of the ceramic cap system meant that it could be adapted to nearly any metal fabrication challenge where rapid, permanent connections were required under production schedules that could not accommodate traditional methods. By June 1945, Nelson's company had expanded its customer base to approximately 600 industrial facilities across multiple sectors beyond shipbuilding. This expansion demonstrated that the innovation possessed commercial value that would persist after wartime demand subsided. Manufacturing engineers recognized that the productivity advantages Nelson had discovered were not specific to military production, but rather represented fundamental improvements to metal fabrication processes applicable across the entire industrial economy, suggesting that the technology would continue generating value during the peacetime reconstruction and development that would follow the war. The patent record documenting Nelson's innovations between 1938 and 1952 reveals a systematic progression of technical refinements that transformed a single insight into a comprehensive welding system applicable across diverse industrial applications. The first patent application, filed in 1938 before his employment at Mare Island, protected the fundamental concept of using a ceramic containment device to hold flux powder during stud welding operations regardless of gravitational orientation. This initial filing demonstrated that Nelson had recognized the core problem and conceived his solution earlier than the March 1941 timeline, when he attempted to convince Navy supervisors at Mare Island, suggesting that his innovation had undergone extended development and refinement before he formally proposed it to the Navy. The December 30th, 1941 patent issuance, occurring just 23 days after Pearl Harbor, provided legal protection at the precise historical moment when wartime demand would make the technology commercially valuable and strategically significant. The timing appeared fortuitous, but reflected Nelson's systematic approach to protecting intellectual property before attempting to commercialize his invention. The patent documentation included detailed technical drawings showing the ceramic cap design with precise dimensional specifications, flux powder composition formulas, and electrical parameters for the welding process, including current amperage, voltage levels, and arc duration timing for different stud sizes and base metal thicknesses. Subsequent patents filed through 1952 protected incremental improvements and alternative implementations that extended the technology's applicability. Nelson developed variations in ceramic materials to accommodate different base metals, including aluminum alloys, stainless steel, and various carbon steel grades that each presented unique welding challenges. He refined the electrical control systems to improve arc stability and weld consistency, addressing issues that had emerged during high-volume production applications where reliability under variable conditions became paramount. He created specialized designs for specific applications, including maritime environments, where corrosion resistance was critical, and heavy industrial settings, where extreme mechanical loads demanded maximum connection strength with safety margins exceeding standard specifications. The drawn arc stud welding process, which Nelson developed as an enhancement to his original design, represented a significant advancement in the underlying welding physics that governed the metal fusion process. Traditional stud welding relied on capacitor discharge to create instantaneous high current flow that generated intense heat rapidly, but with limited control over the thermal cycle. Nelson's drawn arc method used a controlled arc that could be sustained for precise durations, allowing better control over heat input rates and cooling rates that affected the metallurgical properties of the weld zone. This improvement expanded the range of materials that could be welded successfully and improved the metallurgical quality of the resulting connections by reducing thermal stress and minimizing the formation of brittle microstructures that could compromise long-term reliability. The technical principles underlying Nelson's innovations were accessible to any competent welding engineer familiar with arc welding fundamentals. Yet the specific combination of ceramic containment, flux composition, and electrical parameters required extensive empirical development that competitors could not easily replicate without infringing on the patent protections that Nelson had systematically established to protect his commercial position. Mare Island Naval Shipyard reached its peak employment in 1944, with approximately 50,000 workers operating continuously across 3 shifts, representing more than a 4-fold increase from the 12,000 employed when Nelson had worked there as employee number 3,872. The facility that Commander David Glasgow Farragut had established in 1854 as a modest repair station had evolved into one of the Pacific Coast's most significant industrial complexes, its transformation accelerated by wartime demands that required unprecedented production capacity. The wartime expansion transformed not only the physical infrastructure, but also the surrounding community of Vallejo, which swelled with workers and their families drawn by defense industry employment opportunities that offered wages exceeding what most had earned in peacetime occupations. The shipyard's production record during World War II demonstrated the full mobilization of American industrial capacity applied to naval construction. Mare Island constructed submarines, destroyers, and various auxiliary vessels while simultaneously maintaining and repairing ships damaged in Pacific combat operations, creating a complex logistical environment where new construction competed with emergency repairs for resources and workforce allocation. The facility built 44 submarines during the war years, each one benefiting from the productivity improvements that innovations like Nelson's stud welding technology had enabled by eliminating bottlenecks that had previously constrained production schedules. The final submarine constructed at Mare Island was USS Drum, completed in 1970, representing over a century of continuous naval shipbuilding expertise accumulated across generations of workers and technical specialists. The designation as California Historical Landmark Number 821, awarded in 1960, recognized Mare Island's significance in California's industrial and military history as a facility that had contributed to national defense through multiple conflicts spanning more than a century. The recognition came during a period when the facility remained operationally active, but had already begun the gradual contraction that would characterize its post-war trajectory as peacetime defense budgets reduced demand for new construction. The workforce that had peaked at 50,000 during wartime had stabilized at approximately 10,000 by the 1960s, still substantial, but reflecting the reduced production demands of peacetime naval operations that required maintenance of existing fleets rather than rapid expansion. The National Historic Landmark District designation in 1975 expanded the recognition to encompass the broader collection of historic structures and facilities that comprise the shipyard complex. This designation acknowledged not merely individual buildings, but rather the entire industrial landscape that had supported American naval operations for more than a century, including the original facilities dating to the shipyard's founding, as well as the massive expansions completed during both World Wars that had transformed the site into one of the nation's premier naval construction facilities. The closure announcement in the early 1990s reflected strategic decisions about naval infrastructure that extended far beyond Mare Island's specific capabilities or performance record. The end of the Cold War had reduced requirements for the extensive shipyard network that had been necessary during periods of global military competition when the United States maintained substantial naval forces across multiple oceans simultaneously. Ted Nelson's transformation from employee number 3,872, earning $11 per day, to the founder of a technology company that revolutionized industrial welding represents one of World War II's most significant, yet underappreciated innovation stories. The man who Navy supervisors dismissed in March 1941 as an overreaching machinist had created a technology that would save 50 million man-hours during the war and establish welding practices that remain industry standard more than 8 decades later. The journey from rejection to validation, from garage experimentation to Army-Navy Excellence Award, demonstrated that transformative innovation could emerge from shop floor workers who understood production inefficiencies through direct observation rather than exclusively from credentialed engineers working in research laboratories. The financial transformation paralleled the technical achievement in dramatic fashion. Nelson's garage investment, funded by the modest savings accumulated from his machinist wages, grew into a profitable manufacturing enterprise that generated substantial wealth during the war years and sustained prosperity for decades afterward through licensing arrangements and equipment sales. The company he founded continued operating long after his death, manufacturing equipment based on the principles he had discovered while watching submarine deck installation at Mare Island. The technology that began with ceramic caps and improvised welding equipment evolved into sophisticated systems used across global manufacturing industries in applications ranging from bridge construction to high-rise building assembly to automotive manufacturing. The broader lesson of Nelson's story transcends the specific technical accomplishment of solving the overhead welding challenge. His experience demonstrated that institutional resistance to innovation often stems not from technical inadequacy of proposed solutions, but rather from bureaucratic procedures and hierarchical assumptions about where expertise resides. The Navy supervisors who rejected his initial proposal in March 1941 were not incompetent or malicious, but rather constrained by institutional assumptions about proper channels for technical advancement and risk management protocols designed to prevent adoption of unproven methods in critical military applications. The wartime emergency created conditions that allowed Nelson's second approach to succeed, where his first attempt had failed. The desperate need for production acceleration in January 1942, following Pearl Harbor, made Navy procurement officers receptive to demonstrations they might have dismissed during peacetime, when extended evaluation periods seemed acceptable. The technology itself had not changed between March 1941 and January 1942, remaining functionally identical in both presentations. The strategic context, however, had transformed completely. Pearl Harbor had eliminated the institutional luxury of cautious evaluation and extended approval timelines, replacing peacetime deliberation with wartime urgency that valued immediate productivity, gains over procedural compliance. The story concludes where it began, in Building 46 at Mare Island, now preserved as part of the historic shipyard complex. The structure that once housed the submarine construction bay, where Nelson identified an inefficiency that changed industrial welding practices, stands as a monument to American innovation during the nation's greatest mobilization. The wooden decks that once required 12 men working 5 to 7 days to install became historical footnotes in a larger narrative about how individual initiative, technical insight, and wartime necessity combined to create lasting industrial transformation.